Hello, this will be a demonstration of proposition 8 from book 4 of Euclid's Elements, which requires us to, in a given square, inscribe a circle. What we are given then is a square, A, B, C, D, A, B, C, D. So this is a square, which means that these are all right angles. This will be important later. Oh, and it's also equilateral, of course. And the task before us is to inscribe a circle in this given square, A, B, C, D. We begin by bisecting two sides, AD and AB. We're going to bisect AD at the point E and bisect AB at the point F. We do this by proposition 110. Now, it doesn't matter which sides we do, but what does matter is the relationship between the two sides that we bisect. Namely that they are adjacent. So we couldn't, bisect AD and BC and work with the prop, but we could just as easily do AD and DC. Doesn't really matter as long as the two sides which we bisect are adjacent. And now through these points of section, through these points of bisection, we will draw parallel straight lines. So beginning, through the point E, we shall draw the straight line E, what is this one called? EH, right? And so this straight line will be parallel to AB and CD. We can do this by proposition 131, of course. And then next, through the point F, we're going to draw the straight line FK, parallel to either AD or DC. It doesn't matter which one we make it parallel to, because if it's parallel to the one, it'll of course be parallel to the other. And we'll call the point at which these two straight lines EH and FK meet. We'll call this point G. Now, we know that AB and AD are equal, right? This is obvious. They're two sides of a square by definition 122. We know that a square is equilateral, so these two sides, AB and AD being two sides of a square, will be equal, which means that their halves will naturally be equal as well. That's a property of magnitudes, that halves of equals will be equal as well. And we have halves. We have AE, which is half of AD, and AF, which is half of AB, and AB and AD we established were equal. And so their halves, AE and AF, will be equal. Now, knowing that the figure right here, AG, is a parallelogram, we know by proposition 134 that its opposite sides will be equal, so that EG is equal to AF and AE is equal to FG, which means that ultimately by common notion 1, we can say that EG and FG will be equal to each other. Now we can prove in a similar manner that the other straight lines coming from the point G will be equal. So that means that EG, FG, HG, and KG will all be equal to each other. Again, using similar logic that we have equal straight lines. So like, for example, AD and DC will be equal, which means that their halves, DE and DK, will be equal. And these halves are equal to their opposite sides, GK and EG, which means that the remaining two sides of this parallelogram will also be equal. And so all four of these straight lines meeting at the point G, all the straight lines EG, FG, HG, and KG are equal to each other. This is just all by common notion 1, which means that if we describe the circle with the center G and the distance, let's say GE, we know that this circle by proposition 3.9 will pass through the remaining points F, H, and K. And so we'll actually describe such a circle. With the center G and the distance GE, we will describe the circle EFHK, like so. We do this by postulat 3, obviously. And finally, we know that all the angles at E, F, H, and K will be right angles. How do we know this? Well, we know that, for example, EH is parallel to DC, which means that by proposition 129, the corresponding angles will be equal to each other. In this case, that would mean that the angle AEG is equal to the angle EDK. And we know that the angle at D right here is a right angle because it's an angle in a square. And so whatever it's equal to will be a right angle, and so the angle AEG is a right angle, and that means that the other angle, GED, is a right angle. And we can prove in a similar way that all the angles at F are right angles, all the angles at H are right angles, and all the angles at K are right angles. And now, being right angles, we know that these sides of the square will be touching the circle, right? Because we know by the porism of 316 that the straight line, which is perpendicular to the diameter of a circle, from its extremity will be touching the circle. So for example, AB is perpendicular to the diameter FK at the point F, which means that we know that the angles it makes with FK, in this case the angle AFK and BFK, all those angles will be right angles. Well, of course they're going to be right angles, and being right angles, we know that they're going to be touching the circle, again by the porism of 316. And all of the sides of the square touching the circle, we can say by definition 4 or 5 that this circle, EFHK, has been successfully inscribed in the square ABCD, which is in fact what we set out to do. We set out to, in the given square ABCD, inscribe a circle. In this case, such a circle, EFHK, has in fact been inscribed QEF. I have nothing to add to this proposition, so I will simply move on to 4.9.